Right guys, this is the final section of the capacitors topic. I'm going to break it into two because it's a big topic. We are going to look at two key parts of it, but it's really about how things change with time. So here I have my favourite starting place, which is rabbits. But pretty much most natural systems change in the same way. This graph gives us the growth of COVID-19 infections, for example. So we're going to look at this idea. Some of you have already covered it in further maths, but it's a big important idea. There's a bit of maths to get used to as well. So let us start. What we have here is an exponential growth curve. Okay, doesn't tend to be what we're looking at, but many systems have. So for example, the curve has a particular shape. That's what makes it exponential. And for me, the rabbits idea is quite useful, I think. So if we have two rabbits, you know what rabbits do? The population tends to grow. If we've got 4 rabbits, well, what's happening is the growth is now twice as big because there's 4 rabbits able to mate, whereas down here we've only got a little bit. And if we've got 6, then again it's going to be growing at 6 times the rate it is, sorry, at 3 times the rate it is of 2 of them, because there's 3 times more rabbits. So the angle of the graph, the growth of the graph, the change in this number, n, number of rabbits, depends literally on the number that we have. And that's what defines an exponential. So let's go into detail. Exponential changes, here we go. What we're going to look at tends to be changes that go down, so it's a slightly different thing. But whatever you look at, for example, one here, rise in debt. The more people in debt, or the more you are in debt, the more quickly you tend to go in debt. This is Australia in a certain time span. If we were to think of other systems, then some systems get smaller. Okay, bacteria grow in number, populations tend to grow in number, but also what you can find is when things affect it, it will go down. So the idea can go up, can go down, but the crucial bit is the change of rate is constant. Okay, so it's not about fractional stuff, it's actually about quantities of fractions, or quantities of vulgar fractions if you're growing instead. So what we've got in this system, for example, let's just take a couple of values. Here, for example, we've got 0.8. What I'm going to do, just to make it easy to see on your graph, I'm going to go 0.1 above and 0.1 below. So this graph takes a certain time for that to drop down. At that average gradient there, it drops down at a certain rate. If I go to 0.4, okay, so we've got our system there. Well, again, I'm going to go 1 up and 1 down, and what you'll find is that length here will be exactly twice the length of that. So the gradient must be half as big because the number I've got here is half the number. Here, half the number that was there. Okay, so whatever this number is, let's just call it n, let's stick with that. What we've got is, I'll put it into mathematical terms, so there's our change in time. Well, that's changing to lots of change in time. Okay, over that overall gap there. So what that leads us to is a definition, which unfortunately is on the next page, but there we go. And for this, basically, we're going to look at the rate of change of n over time is proportional to how much you've got. Okay, now this can be growth or this can be decay. Okay, so we're going to be mainly looking at decay, and I'll show you why, because in a way it links in with these graphs. It's the decay of current that matters, the decay of the rate of flow of charge in capacitors. So for a decay curve, okay, oh, excuse me, can't spell. For that one, the only difference is you end up with a negative gradient. Okay, so that's rate of change over time. So that is a gradient description. Okay, so they all keep linking back to these graphs. A really good example might be the idea of water pouring out of a tank or pouring out of a bucket, or, because I can draw it better, a tyre. So if you have air, we have a certain amount of air, let's call it a volume in there. Well, if we get a hole in the side, then air is going to obviously flow out of it at a rate of a certain amount of volume per second. When that is twice as full of air, it's going to come out twice as fast. As you get less and less pressure inside, you're going to get less and less change in pressure, difference in pressure inside and out, and so the amount leaving, the volume leaving a second, the number of particles leaving per second is going to get less. Okay, so quite a nice idea to understand how pressure makes a difference on that change of flow of particles. Well, it could be the same with all. For what we're going to do, this graph is going to appear in lots of different places. You may recognize this because this is, for example, half-life. So if you have a nucleus that is unstable and it's half the size, then it's going to decay at half the rate of one that's bigger. Okay, so it all keeps linking up with different things. However, we can also look at changing the axes, which makes this a nice linear graph as well. And this idea, changing the axes, is what's used in a lot of things like astrophysics. We change the scale. So lots of connections come from what we mean by an exponential change. So let us look at a couple of factors. We are going to look at capacitors, obviously, to start with. And what we're going to look at here is what affects that rate of change. Now, if we have this thinking in terms of charge, then the rate of change of charge, current, depends on how much charge you've got. But of course it depends on other factors as well, and if you think about it, it's going to depend on two main factors: how much charge you've got, and also how quickly that charge can escape. Okay, so what it depends on in terms of what we're looking at is the time, the rate is going to depend on capacitance, because that is proportional to charge stored, okay, and resistance, because the bigger the resistance, the slower the rate of flow of charge. Okay, and there is actually nothing else that depends on that. And so we can define the time constant, the rate of the change, okay, in other words, the gradient of the graph only relates to those two factors. So we can give it a constant which defines how steeply that drops down. And that is known as the time constant. Okay, time constant is given a nice symbol which is tau. Okay, so capital T in Greek as such, and it simply depends on C and R, nothing else. Okay, now the way that SI units works means that if we were to take one of those graphs, then what we get is we can find C and R off a graph because of the way it works. Now, I'm going to come back to this in a second in a more mathematical way, but what it does is it basically relates on those two, which gives us this. So as a concept, if we were to look at a graph, the initial discharge gradient, in other words, the gradient at the top, if it discharged at that steady rate all the way, like we did in the practical when we adjusted the resistance, okay, to try to give us a steady rate of flow of charge, steady current, then what we found was, instead of taking a long time, it actually cut down fairly quickly. Okay, so that original gradient gives us a very definite time. If we have a bigger resistor, then according to that equation I've just given you, it will take a bigger time. Okay, so less rapid rate of flow of charge would be more gentle gradient, which would take us back over here. Okay, if I got a very little resistance, it would drop really quickly and it would go down to about here. So we can relate it into these, and what we end up with is we get a very definite value. So I'm going to ever so cheat slightly because I've already got my things labelled on, and I'll show you why. But if you take a line from 4 and you take it back to the original point up there, what you'll actually see, hopefully nice and clearly, is that is the gradient at the top. So this is the initial gradient. That doesn't show up very well, excuse me. Okay, the initial gradient. Lines merging with eyes. And so that will give us a certain amount. That will give us a certain time. Now in reality it doesn't decay that much. What it does decay is much less. However, it is a very fixed proportion. Okay, so for all things that have a natural decay, they will all give, if you took the original gradient, the initial gradient, you'll always find it changes by the same amount. And this is true for radioactive decay. We use something more convenient there, the half-life, but actually mathematically this makes more sense, kind of a bit more logic to the reason. So what we can do is, if we do that, it'll drop to 37% of its original value. Okay, so 0.37 of that maximum charge. If we measure current, we'd get exactly the same thing. After one time constant, we'd have a value of 37% of the maximum current. Likewise voltage. Okay, so what we can do is try to get a gradient, or more simply memorize that number, and we'll work out why that is in a second. Okay, so we'll come back to the maths of it. However, critical point, you wouldn't trust that if you were to do that in an exam. So if you were to try and find out whatever that value is, and 0.37 of that value, that will give you a rough idea. You should always double check it. So what you want is 37% of that new value, and that will come across, and that should give you the same gap again. So if this is 4 seconds, there'll be another 4 seconds to drop to 0.37 squared. Okay, so as I said there, always double check if you're doing this on a graph. And if we say that, then that should give us a more accurate value. Now, we don't always have a graph because, to be honest, this isn't a great method. It is the reason for it, and it's quite easy to see, I think clearer to see, but it doesn't actually work very well often. There's a far better way, which is, of course, to use mathematics. So, what I'm going to do is jump onto the quantitative treatment. How do we actually get that to work? So what we can do is start thinking about what's actually happening inside, and we can use the logic on that last section. So, as it says here, we could use it, but even if you've done it really carefully. Okay, so we're going to derive it using the idea of quantity of charge flowing out of the capacitor, okay, and how it depends on what was left behind. So because of that, we're going to look at that total quantity. We're going to need to integrate it to get us totals. Okay, so going to integrate the charge with respect to time. We could do it for voltage, we could do it for current, we could actually use either of those. However, charge is what causes it to happen, so we're going to go with that. Okay, so let's use the logic of that graph and our definition right at the top of that. Okay, so if we start off the decay, so negative dq by dt, okay, so our rate of flow of charge, current in other words, is going to equal how much charge we got, so it depends on that, and more conveniently we're just going to put in a constant. Okay, so what we need to do, if we need to integrate, then we need to move it around and find various factors. So I'm going to put the q's together, so I'm going to take q across. So I've got 1 over q dq. Okay, I'm going to take that across, so I've taken the minus to this side. It just makes it ever so slightly easier. Not a lot, but slightly. Okay, so here we have a format where we can actually integrate with respect to q. The time we can integrate with respect to time as well. T we can do in respect to time. Start that again. So we can see how charge changes compared to the time change, or for the same time change. So we are going to go to integrate all that. But we need limits because we need to know where we're going from and going to. So what I'm going to do is we have, I'm going to put 1 here because k is a constant and minus is a constant, so we can take that out of the function. And what we're going to do is use the idea to go from some point at the beginning. Okay, so we're going to go from time 0 up to a certain time. We're going to use this to find out how we get the value of q after whatever time it may be on the graph. So we're going to start at beginning of time, the value is at q0. Okay, and it's going to go to some other value of q. Okay, so after time t, we'll have a value q. We want to know what that is. So, if we just link it all together then, we need to do that integration. And again, if you want to drive ahead, by all means at this point from now on, it tends to flow, but I'll show you the kind of key steps, because certain ones are really useful. So I don't know if you still use this convention in maths, but we use square brackets after you've integrated something. Now 1 over q is one of those special factors. It integrates to a certain value, and that certain value is a natural logarithm. So ln rather than log, because that log tends to be at the base 10, so natural log is ln written, q plus some constant, because we don't know what that constant is, and it goes from value q, to value q from q0. Okay, now just to bring that maths in, okay, just to do a little side view on logarithm. Again, on your calculator you've got 2, so you've got log x, or log whatever, and you've got ln. They both work in similar ways, but one is based on, this one is actually based on 10, whereas this, more correctly or fully written, is log to the base n of x. So that would be log to the base 10 of x. Now, if you think about numbers, we go up in base 10, which is looking at columns 7, 6, 5, 4, 3, 2, 1, 0. We have 10 values. There all our digits can be. Works great for decimal. If this was base 2, then it worked really well for bacteria, for example, because they double in number every nth. Base 2 is also computing. Of course, those that do computing, binary language. However, the values, I suppose we should say also base 16 as well for some who are into hexadecimal, etc. This number here is the rate at which all natural systems decay, and that's 2.713. Okay, so bit of an odd number. It's important. It's a bit like, it's an equivalent of pi. It's one of those unique numbers. And that means that instead of things doubling over time, they actually go up by a factor of 2.7. Okay, you may have heard the expression 2.7 kids. That's where it comes from. Keeping sustainability in population growth. If you have more than 2.7 kids on average, then the population grows. If you have less than 2.7 kids, population decreases. that's on natural growth without limitations on food and so on, and diseases. So kind of a natural system curve. Everything changes in that way. So back to this. Let's just do the mathematics and then we'll finish this video in a sec. So take the minus k, because we keep that out. We're going from that. We have 1, integrate that. I'm going to increase, that's t to the power of 0 if we think about that. So I increase the power of t, so it gives t to the power 1, or t. And that's going from our value of t to 0. Okay? So what we end up with here is actually the constant will disappear because we are going to subtract one value when it's inserted into the equation from the other one. Okay, so we end up with log of q, okay, minus the initial value q0. Okay, and for this we're going to end up with minus kt at the top, subtract 0. Okay, which obviously we can ignore. I should say plus c minus c. C's disappear as well. So that is a really useful form of the equation. Okay, there's different ways around it, but another way of writing that, which is the exact equivalent, that's what calculators do, I should say, when they're doing calculations on logarithms in your calculator, it converts them in and then subtracts them or adds them. For us, we tend to write it as the equivalent version, which is the log of the ratio. So if you're subtracting logs, it's the same as dividing numbers. So subtract by that one means divide by. If we do that, you'll get exactly the same system. So calculators and computers, what they'll do is if you want to divide numbers, they will get the value for each of those and then subtract them, because computers can basically just add or subtract. That's what their functions are based upon. Over here, more simply, still minus kt. Okay. Now, what we find from this to make this work is that k has to be, so back up here, this is the initial rate of decay. Oops. Okay, so that's what gives us that gradient for this. Down here, by the time we get to this initial rate of decay, or decay rate, fit it in more simply, is equal to 1 over time constant, okay, which equals 1 over CR. If you have a bigger capacitor, it takes longer, it's a slower rate. If you have a bigger resistor, again it's a smaller rate of decay. So increasing either of those will actually make the rate of decay slower. Now what we can translate this as, again both of these are equivalent versions of the same thing, but what they relate to is they can both rearrange into a more, shall we say, neat version. Okay, if I want to get rid of this logarithm, I have to take the second function, the opposite function. If you look on your calculator, the opposite function is powers to the base, the natural base, which is at 2.7. So what we end up with is q over q0 equals e to the minus kt. Okay, that, excuse me, q0, that is our full equation that you've got in your data book, more neatly done. The charge at any point scaled up by your initial amounts that you've got, e to the minus t over CR, if we bring it all in together. Okay, now that is our fundamental equation that describes how the value of Q changes over time as it decays exponentially. Okay, decays minus exponential. If I had a plus, I would get exponential growth, which would be my gradient increasing, increasing, increasing. Okay, capacitors do the opposite. Flip it around, the time goes backwards, they disappear down and flatten off. Okay, so fundamental equation. Okay, I'm just going to link it in because in your data book there's a few more versions which I have put down here, but we'll get the explanation, so I'll just skip that a second. If you're to think of that as time, well, current, maximum current is Q over T, current at any point is Q over T, so actually you can write the same equation as current. So please notice that I equals I naught e to the minus t over CR. Okay, or personally I think this is the most useful, you can measure voltage, and voltage is proportional to Q, so again you end up with a definitive equation which is V is V naught e to the minus t over CR. Okay, and that, you know, links into what we said before, etc, etc. So V on your capacitor is that. Now, to round this off, let's just take it back to where we got those numbers from. Okay, so if after one time constant, so if t equals one time constant, then what we end up with is a way of giving us a more accurate value. So at that point, Q equals Q naught e to the minus, say, t over CR, but t equals CR. Okay, so for that, we're obviously going to end up with Q equals Q naught e to the minus 1. And if you put that in, what you'll end up with is Q over Q naught equals e to the minus 1. E to the minus 1 is 0.37. So that's why you've got, as a fraction of the value, fraction of the original value, it'll be 37%, 0.37 of. If you go to the second time constant, again we can check that in, what we'll end up with, I can do this a little bit easier, Q naught e to the minus 2. Yeah, because that will give us that same point. So let's say 2 lots of t over CR, in other words 2. So if you put that in, Q naught e to the minus 2, Q over Q naught equals 0.14. Okay, and that's where you got these values. Now, we'll find if you're growing, if your capacitor is charging up, then perhaps 0.37 is not so useful. You might want to think of the change instead. So after one time constant, I tend to think of that number instead. So you'll need to remember it. Unfortunately, there's no way of calculating it easily, so you might as well just do it fully, or just memorize that that's a 0.63 drop change. Okay, and that will always be true even if it's growing. So if it's growing after one time constant, it will have gone up by 0.63. If it's here discharging, it goes down by 0.63 after thing. Okay, and again, that's 0.63 of that total value there. So kind of convenient. Just want to pick on one final thing, which is because these three graphs are the same form on your data sheet, you'll get it written as X, a random X, proper maths version. X naught still, whatever that value is, so current, charge, or voltage minus T over CR in the data book. Okay, brilliant. Let's take a pause, and I suggest this is where you have a bit of a think about that, and then we'll derive the second part.